Yo, what is up, guys? Welcome back. I have a little announcement. I think, considering this is kind of like one of the first weekends and I'm here, I think I'm gonna do my first ever programming contest today on Leetcode. Now I know, I think that's a big step up, right? But do I think I'm gonna do well? Probably not. But I'm at least pretty confident. I think I'd be able to solve at least one or two problems out of like the 3 or 4 that they give, and I'm not really 100% sure what they give. I think they give 4 problems. So I'm excited about that. But I just kind of want to feel like my level and kind of see where I'm at. This is going to be a GMT, whatever, right? Whatever this time zone is, I think. Oh, GMT time. Greenwich Mean Time, Saturday. Okay. So it starts in 9 hours and 45 minutes. Now I'm pretty sure that's probably about 10 o'clock my time, maybe 9:30 or something. So I'll let you guys know tomorrow how it goes. Penalty of 5 minutes will be applied for each wrong submission. Jeez, man. Yeah. My goal is I'd be happy to get one problem correct. Or 2 problems. I'd be pretty happy with that. I kind of want to just see where my level's at. Kind of just see what happens. So it's a little bit of an announcement. I'm gonna actually register right now. If you can't participate, unregister with consequences. Your rating stays safe. Okay, register. Has begun sharpening your skills with past questions. Start practicing. Okay. Maybe I could practice later, but we're registered right now, so pretty excited about that. But yeah, we're just gonna get to some problems today. Just another usual day. Hopefully I'd be pretty happy if we get some nice problems in the thing. Maybe I don't know, stuff we practiced before, so we can kind of apply those skills. But knowing my luck, it'll probably be something super odd. But we'll check out the sum. Let's check out this. The XOR total of an array is defined as the bitwise XOR of all its elements, or 0 if the array is empty. For example, the XOR total of the array 256 is 2 XOR 5 XOR 6 is equal to 1. An array A is a subset of an array B if A can be obtained from B by deleting some possibly 0 elements of B. An array A is a subset of an array B if A can be obtained from B by deleting some possibly 0 elements of B. So we have subsets of 1, 3 are the empty set of a XOR total of 0. 1 has a XOR total of 1. 3 has a XOR total of 3. 1, 3 has a XOR total of 1. XOR 3 is equal to 2. 0 plus 1 plus 3 plus 2 is equal to 6. 0 plus 1 plus 3 plus 2 is equal to 6. Okay, so we always have to calculate the empty set, right? So, okay. So how can we do this, right? You gotta go through each element. The XOR total of an array. Okay. I'm honestly really not sure where to begin on this problem. Try to think here. Oh, whoops. Oh man, where to begin? Can we use recursor to efficiently iterate through all the subsets? Okay, can we use recursion to iterate through all the subsets of the array? When we think about subsets, we think of backtracking. So we would start with an empty list, add one, pass in nums, right? Call our backtracking, right? We'd probably want to return backtracking, pass in, I guess, we want to pass in nums, right? And maybe our first element. Like the nums -1. We just would return 0, right? Because 0 plus everything is nothing. So I think we just return 0. Otherwise, we would want to subset result totals. Okay, so if I is equal, let's do the length of nums. And we just return cur, right? Which is just our current count, right? Let's call it cur count. Right. If not, in backtracking, we'd have to look at the previous and then the one ahead, right? So I'm pretty sure we just call our backtracking function. I just don't know what this should be here. Like, man, Dunkin' coffee is so ass, dude. Like, seriously. Okay, let's look at the.
Think your taxes are simple? You could file for free with H&R Block. More people qualify for H&R Block free online than TurboTax free edition. Find eligibility requirements at hrblock.com.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, sum of all subset XOR totals. So this is an easy problem, but there is a solution to this problem that is pretty damn hard, I would say. So I'm going to go ahead and show you the probably intended solution that makes this an easy problem. It's not going to be like the most efficient, it's going to be exponential, and I'm also going to show you an optimal solution, which I will warn you is pretty mathematical, and I'll even admit to you that I actually wasn't able to come up with it by myself. I didn't know that an efficient solution actually existed for this problem until I skimmed the editorial, but I recognize that that editorial is pretty difficult to read, so if I can make it any easier for you to understand, I'm happy to do so. But let's get started with this problem. Kind of like yesterday's problem, it's all about the XOR binary operation. Basically, we're given an array of elements. I'll take the second example, it's a bit more interesting, 5, 1, 6. We want every single subset of these elements. Now, remember, subset is not the same as a subarray. If we were only talking about subarrays, then we'd have roughly n squared subarrays. But with subsets, the idea is different. We'll have about 2 to the power of n. And the reason for that is, with a subset, we have a choice for every single element. We can either choose to include it or not include it. So if I just wanted to show you what every single subset from this looked like, I would do this. I'd say, okay, first time we include 5, and we can also skip 5. And then we can include 1, and then we can skip 1. We can include 6, we can skip 6 over here, and we can include 6 here, and of course skip it. Same thing over here. I'll just quickly draw it out. Here we're at the second choice. We can either include 1, skip 1. Here we can either include 6, skip 6, and same exact decision down here. Now, if you
include 5, skip 5, include 1, skip 1, include 6, so 5, 1, 6. Or we do 5, 1, skip, 5, skip 6, 5, skip.
take any one of these root to leaf paths, you will have a different subset. Even though the input elements could be duplicates, so like even though like 2 sets might have the exact same values, they're still technically different subsets. So if you count all of these, you're going to see we have, I think, 8, right? So the reason for that is we branch by 2 every single time. If you look at the height of this decision tree that I have, it's a height of 3. Therefore, we're going to get 2 to the power of 3. That's going to be 8. There's 8 different subsets that we can form, and if you look at one of them, it's an interesting one over here where we literally didn't include any element. So that actually does technically count as a subset. So that subset, in the context of this problem, which I guess I should talk about, for every single one of these subsets, we want to take all the elements and XOR them together, and then we'll get a result. So if we were to XOR, I think, these 3 together, we'd get something like this. Well, actually, let me start with the other one. If we were to XOR nothing together, like there's no elements to begin with, then obviously that's going to be 0. This one over here, where we have nothing but a single 6, the 6 by itself is just going to be 6, right? This one over here, 6 and 1, if we were to XOR 6 and 1 together, what would we get? Well, in the binary representation, 1 looks like this, 6 I think looks like this. So if we XOR them together, I think we actually get 7. So for each of those, we're going to end up adding all of them up, and that's the result that we're trying to return. So for any given subset, XOR all the values and then for that, get that total, and then add all those totals up. So we'll have 8 numbers. One of them is definitely going to be 0, and then we'll add all of them up, and that's what we're trying to return. So obviously, the brute force solution of this is recursive, and time complexity is going to be 2 to the power of n. To implement it in terms of code, obviously we have to keep track of which position we're at in the input array. I'll use a parameter I for that. In terms of implementation, there are different ways that you can do it, but I think the easiest way definitely is to just keep track of the total of like the XOR values as we go. So like by the time we're here, the total is obviously 5. When we're here, we have nothing. The total is initially 0. When we're here, we are going to take the original total 5 and XOR it with 1, and then we'll have a new total, and then we'll kind of keep track of that total. And then by the time here we get to the base case, we'll know we're at the base case because we're at the end of the array, and then we can just return that total. And obviously, we're going to have 2 recursive calls because we're branching in 2 different directions. So I'm going to go ahead and code this one up first. So I like to have a little recursive function. I'm going to call it DFS. And like I said, we're going to have 2 parameters, I and just keeping track of the total. As you can imagine, the way we're going to call this DFS is starting at index 0 and having our total initially be 0. And then we're going to return the result of this. And we expect this to compute
We
the
got
total.
that. We just don't know how to do
Here,
the
what
recursive
I'm going
part.
to do is say, first of all, the base case you can imagine is going to be what I said. If I is the end, then let's just go ahead and return the total. Otherwise, we have 2 choices. I want to be very explicit with what we're doing here. We have one choice, include nums of I. In other words, we are going to make a recursive call. We're going to say DFS, go to index I plus 1. That's simple enough. Like, we're going to do that regardless. But what's the total going to be? If we include this number, our new total is going to be total XORed with the number, nums of I. That's simple enough. But be very clear with what this function is actually doing. What this function is doing is it's returning the total of all subsets, including this number, every single subset. Because recursively, we're going to make that decision that I'm about to show you. We have the decision to include this number. We have the decision to not include nums of I. And that would look pretty similar. Let's go ahead and fix this. It'd be very similar. I'm sure you can modify it. It's just going to be removing this part of the code. So this is going to be returning the sum of all subsets that do include this number. This is going to be returning the sum of all subsets that don't include that number. And what we want to do is just total these 2 up and then return the result. So that's what I'm going to do. And I'm just going to, I guess, get rid of the comments now and just add these up in the same line because you probably can see what each of these means. Let's go ahead and run this. As you can see on the left, it works, and supposedly it's pretty efficient, but there is a much more efficient solution to this problem that I'm about to show you right now. So I would buckle up because this is going to be a fun one, at least for me, because you guys know how much I love math, and I know how much you guys don't like math, at least most of you. So this is mainly, I just want to say, combinatorics. It's kind of a branch of like discrete maths. It's like related to statistics and stuff like that. And it's also somewhat related to binary, obviously. The idea here is obviously we know for each of these numbers, like we're going to have 2 to the power of 3 subsets. So let's just continue with this example because it's small. So I'm just going to kind of draw like 4 little boxes here. These are going to be each of the subsets. We know that we can either include this or not include it. So half the subsets are going to include 5. Let's say that this row includes 5, and then this row doesn't.
I'm not going to look at the other part, only because I just kind of want to, I feel like that's for a different time. We need to understand we can make include nums is equal to DFS I DFS I plus 1, cur count, plus nums I, exclude nums is equal to DFS. Sorry, well, we'd be backtracking actually, not DFS. Well, plus 1, cur count. And then we add them together, we return. Can I concatenate list, not int? I'm so confused here. No, we'd want 0 and 0. Whoops, didn't change this. That's probably why it's not working. What am I missing here, bro? Thought I, yeah, pretty much have it. Oh my god, I'm not zoring, I'm adding, bro. Jeez. What am I doing? Bro. There we go. This guy doing kills. What is this solution, bro? What the? So he creates a subset, alright? For subset in subsets, subset XOR is equal to 0. If not subset, if not subset XOR, and then they XOR 0 to it, they continue for num and subsets. Yeah, interesting. I kind of want to... Let's actually search some graph problems. Tags, graph. Let's do easy and find the town judge. What is this? In a town, there are n people labeled from 1 to n. There is a rumor that one of these people is secretly the town judge. The town judge trusts. If the town judge exists, and everybody except for the town judge trusts the town judge. There is exactly one person that satisfies properties 1 and 2. Right? Trust, where trust is equal to A1, representing that the person labeled A1 trusts the person labeled B1. If trust in a relationship does not exist in a trust array, then such a trust relationship does not exist. Return the label of the town judge if the town judge exists and can be identified, or return -1 otherwise. So n is our nodes. There are n people labeled from 1 to n. Okay. So I think A label trusts the person labeled B1. Okay. So what are we returning? Okay, so 1 trusts 2, but 2 doesn't trust 1. So then that satisfies that the town judge doesn't trust anyone. So there can't be any outgoing edges, I think. Everybody except for the town judge trusts the town judge. Oh, okay. Okay, so I think this means that... So pretty much it means it has to be... So every other single node has to trust, so it has to have an edge connecting to the value, but the value can't have any outgoing edges to anyone else. I think. Let's kind of visualize this problem. So I think... So we have n is equal to 2, right? Which means we have 2 vertices, right? 1 and 2. And in this case here, 1 connects to 2, right? 1 has a director. This is a director graph. 1 has connected to 2, right? So this here, we returned 2 because 2 doesn't have any... Everybody except the town judge trusts the town judge. So everyone in... So there's only 2 people. Everyone, so there was more, right? Everything would have to point to the town judge, right? But he can't have any outgoing ones, right? So if we look at the next one, 1, 3, 2, 3. So we have 2. We have 1. We have 2. And we have 3, right? 1 trusts 3. And 2 trusts 3. So that means we will return 3 because 3 doesn't have any outgoing edges, right? But how can we write this in code? Okay. Trying to think here. How can we solve this? 997. Find the town judge. Can we make some sort of adjacency list, right? Like we usually do for the problems? Loop through the nodes. Us in trust. The array, right? So we would call ADJ list and we pass in trust, right? For I in array, AB is equal to I. We want to initialize our graph, right? Graph, we create our hashy, right? Then we do, okay, well, A not in graph, then graph A is equal to a list. And dot append B graph B dot append A. We just want to return our graph, right? Graph is equal to this, right? And let's print our graph. Oh no, this would be, yeah, this would be an undirected edge, so we don't want to do both. We just do graph A dot append B. We don't need this one either, I don't think. Let's try this. Okay, so I think that worked. One trust three, two trust three, three trust one. Okay. Okay, we want to check, okay, does, okay, we want to somehow loop through, okay, I don't know if DFS is required for this. Like I think with the director graph, maybe not. See, that's what I just don't. Okay. Let's think about this. We look through each value in our graph, right? So we go through one, and we check. Well, what are its neighbors, right? Its neighbors are 2, right? So then we would I don't feel like all this maybe needs to be done, right? Let's print our node. Okay. A neighbor in graph node, right? Okay, we can make some trust array, right? So we would make like some trust array, right? Rev 0 if neighboring graph node. I think we'd have to initialize our array though to be 0 times neighboring graph node. Okay, so if that neighbor trusts someone, then maybe we can do, well, trust neighbor minus equal to 1. Okay, let's print out trust. This index out of range. Let's check out the neighbor here. Okay. We trust neighbor -1 minus equal 1. Will that print? Okay. So instead of printing the neighbor, let's print trust array. What can we make up with this data? Well, okay. Well, I knew the adjacency laser was a little bit overkill for this problem. I already knew that, but if A trusts B, A loses a point, but if B gains a point because they are trusted. You gain a point if you're trusted, but trust node loses a point. Okay. For I in trust, if I is equal to n minus 1, I is equal to n minus 1, this one, then we return, what do we return here? We return I plus 1. Else, we will just return -1 because no one. Let's print trust here. Oh, we're not even returning anything. That's, oh, we are. and -1 else -1. Is that a... I don't know if that's valid, to be honest, but... Okay, that maybe doesn't work. For I in range. Is equal to n -1, we would return I plus 1. Otherwise, we would just return -1. There we go. I think what makes mine so slow is the adjacency list. Yeah, we could have just... Alright, whatever. Well, it was good practice, you know, implementing the adjacency list, I feel like. Alright, whatever. Let's just go to another graph problem. Just got another graph problem. Oh. You know, I actually recorded this playlist for graphs. Maybe we'll take a look at it really quick. Okay, we got this link here, https://leetcode.com/problem list. Not 2K47 2 pointers, no. You know, okay, this is 2 pointers, right? Let's go on this guy's LinkedIn to see if he has does he show posted. I like this guy's post, man. I don't know what it was, but it was Leetcode cheat sheet. I think this is what it was. Bro. What the hell am I looking at, bro? Dude, I just want to see your Leetcode cheat sheet, bro. Okay, here we go. Let's check out his graphs. Yeah, here we go. Key for solving network connectivity problems. Okay, alright. How do we get the link here? Okay, we got the link. Okay, let's go over here. leetcode.com/problem/9x1UEA1h. Okay, got some graph related problems now. Okay. Surrounded regions, evaluate division, shortest path, and matrix. Okay, max area of an island. Let's take a look at this one. Another Matrix one, bro. Oh my gosh, bro. Ugh. Community times and matrix binary grid. An island is a group of ones representing land connected four directionally, horizontal or vertical. You may assume all four edges of the grid are surrounded by water. The area of an island is the number of cells with a value of 1 in the island. Return the maximum area of an island in grid. If there is no island, return 0. Okay. I'm pretty sure I can solve this one. Again, I think this is just a variation of the BFS approach. This time we loop through every single one, right? We find a 1, okay? And we just keep track. We run our BFS, right? And we just keep track of the biggest island. So I think when we run BFS, really our only change to our algorithm would be that we'd, inside of our queue, we'd also append the max size, I think. Okay. So we take the length of the rows, right? So we can make our rows to be able to length of grid, and our calls to be the length of grid 0, right? There's gonna be many things here. I think we need a set, right? We need a visited set. Or else we're gonna get stuck in an infinite loop, or we're gonna keep visiting each other. We're gonna need a directions array, right? We're gonna need a queue to actually implement that queue, so. Man, why do I keep getting this weird shit on Telegram, man? Okay. So from collections, we want to import DQ, right? So let's create our DQ array. So make Q is equal to DQ, right? We'll create our directions array where directions is equal to, okay. Left, what would left be? Left would be, left would be -1 0. I think right would be 1 0, right? Up would be -1, oh sorry, 0 -1, and then down would be 0 1. I believe this is left, right, left, right, up, and down. Okay. So our first thing here is that we need to add, we need loop through this matrix, and I think we need to add 1, every single 1, right? I'm actually not sure. I believe we'll need to. Okay, I'm gonna quickly go to the bathroom because I have to go to the bathroom. And we'll be right back. Alright, I'm back. Actually, I'm taking a shower too. I like to feel a little bit fresh and locked in. So I believe, like, in the shower, I was kind of thinking, I think our step here, instead of adding each one, right? Because if we add each one to our queue, then we're just going to visit everything, right? So I think what we got to do here is that we got to add, we got to loop over for row in rows, and for col in cols, right? We want to check, well, if row, if grid, oh, whoops, grid row col. Grid row col equal to 1, right? So if this is an island, right? We want to call our BFS function, right? So if grid col is equal to 1, we call our BFS function. So we call BFS, right? We probably want to pass in our row column. Probably want our visited array. Yeah, probably that. Alright. So I assume we probably do our BFS function up here. Def BFS, we want our row, our column, and our visited, right? Okay. Oh shit, probably our queue too, right? We are queue too. Okay, so we do while queue. So we got our queue here. I'm gonna move this a little bit. So while we have something in our queue, we want to pop from there, right? So we want to do what do we want to add to our queue? Well, actually, guess we probably want to add to our queue down here. So we do queue.append row col and probably want to add like a count too, right? This would be the first count here, right? Okay, and then we'd want to do cur row cur col, and I guess we can do our max island is equal to queue.pop, right? So we pop from our queue, then we want to loop through. Well, we need to pass in our direction array, I think, too, right? Directions. Well, we can do for new row and new col in directions. We would want to do our new row, right, and our new col. Our new row is equal to new row plus cur row is equal to new col is equal to new col plus cur row cur col. Okay. Now, what do we want to do with that? I want to check the bounds, right? So we check, if 0 is less than or equal to new row, but is less than or equal to rows. I wonder if we're going to have to reference that in the parameters here. I'm not sure. And 0 is less than, this shouldn't be equals. This should just be and 0 is less than or equal to new col. Sorry, less than or equal to new col, or is less than cols, and new. Let's have a look here. Okay, so we have grid, row call equal to 1, and we need to check if it's not unvisited, and grid row call not invisited. Okay, now we want to check, well, row call not in visited. Okay, we want to add it to visitor, visitor.add, right? Row call. And then we want to add to our queue. So queue.append row call. Wait, sorry, we want to add, okay, wait. New row, new call. We also want to add new row, new call here. Okay, then we do. We want to pass in our time, right? So we'd need to do, well, our original max island +1, right? And we want to check our Yes, maybe we'd want to create like a variable here, like max res equal to 0. And we check, well, max res. We do max island. Max island plus, and we compare it to our max res. But would it have to be before this? That's the thing. Well, I'm going to leave it here for now, so I'm not really sure. And let's return our max res. Then we actually do our res. Let's call it our func res is equal to BFS row call. Then we want to check, well, let's call our okay, let's make our return res here. Our return res is equal to 0. And then we want to do our max here, and we do max return res is equal to return res and func res. We call that max here, right? I guess we want to return our return res. I don't know if this is going to run, bro. There's probably so many mistakes in this code. Like, int object is not iterable. Row in range rows. Range calls. Visited queue directions. What a solution this is, bro. I'm honestly not sure. Visitor.add new row new call. Let's take a look. Few key issues in your current incorrect usage inside the BFS. You're using grid row call inside your BFS loop. Okay, there's our first issue. New row, new call. Visitor check is being done on the wrong conditions. You're checking row call instead of. Okay. New row, new call. Okay. Queue should be created fresh for each BFS call. You're reusing a global queue, which might carry over state between island searches. Reusing a global queue. Your max island count isn't properly contributing to the final result. Somebody that you used to know. You didn't have to cut me up. I need to know. Now you're just somebody that I used to know. Okay, alright, so we return res here. We talk about the global queue. We're passing in a global queue, so. That you used to know, didn't have to come here. Q is equal to DQ. Oh shit, that's inside of that. We don't want to do that. Q is equal to DQ. Alright, then we want to add Q.append. Column directions. visited.add start row start call. Area is equal to 1. If 0 is less than or equal to new rows less than rows and 0 is less than in grid, new row new call is equal to 1 and new row new column not in visited. Then we do visitor.add new row new call q.append. Okay, so we're not actually counting inside the queue. Okay, we're just actually counting here. So, oh, we add our area here, our area plus or equal to 1. We return our area. Oh, whoops, we need row call. Why are we appending directions here? We don't need to append directions. Expected 3, got 2. There we go. Jeez, man, there's a way faster solution than mine. It's the same solution. Okay. Keeps your traversal self-contained. So okay. Okay, that was a good problem. Surrounded regions, get watched by your videos, friends. Is this another BFS, bro? I think this was a recent problem on the problem every day. Problem of the day. Does it tell you this problem was no? Okay, let's take a look at it and find eventual safe states. There's directed graph event nodes where each node is labeled 0 and -1. The graph is represented by 0 index 2D integer array graph, where graph I is an integer array of nodes adjacent to node I. Okay. Meaning there is an edge from node I to each node in graph I. A node is a terminal node if there are no outgoing edges. A node is a safe node if every possible path starting from that node leads to a terminal node or another safe node. Return an array containing all safe nodes of the graph. The edge should be sorted in ascending order. 2, 4, 5, 6. And what is a safe node again? A node is a terminal node if there are no outgoing edges. A node is a safe node if every possible path starting from that node leads to a terminal node. So pretty much we're just, I guess we don't even really have to look at this. We're just looking for a node that has no outgoing edges. I think, right? So they have the output here is 2456. This is a directed graph, so I'm a little confused. Well, 2 has an outgoing edge. So how is that? Nodes 5 and 6 are terminal nodes as there are no outgoing edges from either of them. Every path starting from at nodes 2, 4, 5, and 6 all lead to either node 5 or node 6. So starting from node 1, you lead to 2. Starting from node 1, you lead to node 3. Node 3 leads to node 0, which leads back to node 1. Okay. Okay, so we add in 2 because it leads to a terminal node, right? I understand that. 4 leads to a terminal node 2. But don't all of them lead to a terminal node? Doesn't 1? Because we go from 1, we can go to 2 and then go to a terminal node, so... A node is a safe node if every possible path starting from that node leads to a terminal node. Edo to find eventual safe states. Need to fully understand the problem first. Okay, you're given a directed graph represented as an adjacency list. Your job is to find all the nodes that are eventually safe. What does eventually safe mean? A node is eventually safe if every path starting from it eventually leads to a terminal node, a node with no outgoing edges. Okay. So it's safe, right? So 1 is safe because 1 goes to 5. So 1 is safe, right? 2 1 is safe because it has 1. So the only outgoing edge 3, 0, 1, 2. Because every possible outgoing edge leads to a terminal node. So 1 is safe, right? 3 is safe because every possible edge that goes out. So 3, 0, 1, 2, 5 leads to a terminal node. So 3 is safe. 0 is safe because 0, 1, 2, 5. Okay. Why is 2 safe? But 2 also leads to a terminal node 2. Leads to 5. So how is 2... I don't really understand, to be honest. What does eventually safe mean? A node is eventually safe if every path starting from it eventually leads to a terminal node, a node with no outgoing edges. That means there's no way to enter a cycle starting from that node. Okay. Can we enter a cycle from 1, 2, 0, 1, 2, 0, 1, 2. Okay, there's a cycle here, right? One, 3, is there a cycle at 3? 3, 0, 1, 2. Okay, maybe it's probably easier if I kind of draw this a little bit. So let's create an adjacency list with a hash map. Def adj list. Oh, whoops. Def adj list. We pass in our graph, right? So let's pass in our adjacency list, right? We pass in our graph. Okay. Let's create a graph here. Call graph 2, right? I don't know if we can, I don't think we can call it the same. So we'll call graph 2, right? Passing our thing. We do for I in graph A B is equal to I if graph 2A not in visited, not in graph 2, and graph 2A is equal to a list, alright? Because this is a directed graph, so I need to do both, right? So then we would do, well, graph 2A is equal to graph 2A dot append B. And then we just return graph 2. Right, call it here. And then we just want to print our adjacency list. Print ADJ list. Oh. Key error 1. Not all values from unpack. Expected 2 but got 1. Why do we have single nodes? Why do we have single nodes? Now I just realized that. Why? What the? So 1 connects to 2. 2 connects to 3. Oh. How is... What is this graph? You're given a 0 index 2D array graph where graph I is an integer of array of nodes adjacent to node I. I don't understand, bro. From collections, import default dict. ADJ list. For node in range length graph. For let's do for destination in graph node. ADJ list node dot append destination. Then we just return dictionary ADJ underscore list or ADJ list. Okay, so how the hell did we do that right there? For node and range length graph, so we looped over the graph for each node, right? For destination in graph node, ADJ node dot append destination. Let's print out node here. Okay, so we're just printing the node each time, and then we're looping through this here. Okay, I understand. Okay, so I didn't realize that we're referring to the indice here. So this is 0, 1, 2, 3, 4, 5, and 6. I didn't realize that. Okay. Now we know that. Okay, we built the adjacent list, right? Okay. So really what we messed up with building this with our own code is that we did the same thing, right? But instead we expected an AB, right? But instead we should have just done used I and checked, well, if I not in graph 2. So I think the same thing would have worked. Let's just test it out, because why not? Let's say we had for I in graph, alright? We had our node here. So let's get rid of this, right? Let's do what we did. We did for our I in node, right? Well, let's keep it as node, because why not, right? I in node. Let's create a normal dictionary, right? Okay. And for node in the dictionary, right, we want to do, okay, well, for destination in node, graph node, if ADJ list node destin graph node. Let's print dest. One, two, two, three, 5, 0, 5. Okay, right. So if we're at the destination and it's not in the node, ADJ list node not in graph 2, then we can graph 2, sorry, not in adjacency list, my bad, not in adjacency list, and adjacency list node is equal to this. Otherwise we just append, right? We do adjacency list node dot append destination. Okay, and then we would just return our adjacency list. I believe that should work. Fuck. Maybe this should just be node, if node not in adjacency list. Two, three, 4. Okay, that works, but we're not adding the last one, right? 0, 1, 2, 3, right? We need to probably go here and check, well, if node not in adjacency list, then we need to create it here, I think. Maybe this doesn't need... Maybe this might work. Let's try this. Okay, if if node not there we go. I think this is correct. We can get rid of this default dict now. Oh. Oh my god, dude. There's a minor issue. What is our issue here? Okay, yeah, that's true. I didn't think about that. But we know that it's not going to be initialized. That's what it's telling me. So I guess we can get rid of this if. Actually, I'm going to keep it, right? This is my code. I'm going to keep it. I mean, it's the same thing. It doesn't really matter. It doesn't really... It's unnecessary, but it works, right? Okay. So now we've got our graph, right? So now what we want to do is we want to check a cycle, right? So how do we check a cycle? Okay, so we've got to think about how we can check a cycle on this list, right? So if we go here and we check 0 and 1, I think we should run DFS here, but use DFS to check if there's a cycle, right? Because we can reset our visited set every single time as we loop through our DFS function, right? So we have a local set and we run DFS and we loop it and we see that we can get back to an original node, then that means that loop that we find, we can identify that specific node won't be added to our res array, right? So I think that's the way that we're going to go about this problem. So what we want to do is we want to create a DFS function, right? And we want to pass in, well, we want to start from 0, right? So how can we start from 0? Maybe we need some sort of for loop, right? Maybe like for node in graph, right? Let's print that node, right? For node in adjacency list, not graph, right? Adjacency list. Oh shit, we have to do it under here. Oh, my bad. Okay. 0, 1, 2, 3, 4, 5, and 6, right? Okay. So then we call our DFS function here. We call DFS we call our DFS function. DFS, we want to pass in our node that we're looking at, right? We want to pass in our adjacency list, right? So we create our DFS function up here, right? So we call def DFS. We pass in our adjacency list, okay? Then what we want to do here is we want to do, well, okay, what would be our base case, right? So we want to create a visited set, right? Because we set a local copy, right? So we want to create a local copy each time. And at this local copy, we want to check, well, if DFS, okay, wait, sorry, if, whoops, my bad, we didn't pass in, even not passing our node, right? If node in visited, okay, right, we have found a cycle, right? We have found a cycle, and we can append node in visited, we found a cycle, we can return true, right? Or we can return false, sorry. Okay. We can check here if DFS equal to true, no cycle, right? Then we can append this to our res array, right? So let's create a res array. Right, this is what we're going to return, right? Equal to true, we can append that node to our array. So we do res.append, and we append that node, right? Okay. We go for neighbor in adjacency list node. This would be our recursive function, right? So for each neighbor, right, we're going to I feel like we have to pass in that visited set, right? Maybe we have to pass in the visited set up here. So let's call this set, right? We want to pass in like a set. I think you can do this. I'm not sure. Okay. Because I feel like we have to pass in that set because we have to make it local, right? Because if we keep calling the DFS function, we're going to keep resetting the set and then we're not getting anywhere, right? So if we go for neighbor in the adjacent list node, right? Then we're going to check, well, man, these recursive functions are so tough, man. Oh my god. They're so tough. For neighbor, an adjacent list node, we want to check. Well, do we maybe want to pass in? Well, maybe now I'm thinking about maybe we can pass in 5 and 6 already. Right? Because we already know 5 and 6 are going to be terminal nodes, right? So maybe we have to do that. Maybe we have to pass in a set, right? We have to create a set here. Right, so maybe we can do it here. Like we can do for I in adjacency list. If adjacency list I is equal to this, then we know that this is a terminal node. So then we can do, well, let's do set is equal to, no, sorry, let's do res is equal to set. Then we can do res.add I, right? Okay. I think in this case here, this should print. I'm gonna get a notepad. Let's put in this code here. Put in this code here as well. We get rid of this. We get rid of this. Oh shit, equal. Okay, yes, that's good. Okay, so that works, right? Now we can pass this back in, right? Adds initial terminal nodes, right? Okay. Need to recreate this, so we do, well, for node in graph, right? We want to call DFS node. We want to call our adjacency list, and we want to pass in our res array, right? Okay. We have our DFS function, right? Then we call, okay, for neighbor and adjacency list. We have a base case here. Well, if the node in res, then we just want to return true, right? Node, right? So if we see, well, if DFS neighbor adjacency list and res equal to true, equal to true, then we can just return true, right? Else we can return false. Else we can just, I think we can just do this, return false, right? So then we check in here, well, for node and graph, if DFS node adjacency list is equal to true, equal to true, it's a safe node. It's a safe node. So then we can, oh my god, dude. We can res.append, and we can append that node. Right? We can append that node. We can just append that node. Then we can return the res. Visited is not defined. The fuck? We forgot I visited. Passing a set, right? This could be visited. This is an unhashable type list. Jeez, man, this is some insane. Got the correct base cases, right? None in res will return true. Oh yeah, then we have to add it to visited. Got that visited.add node. Node is processed. Res.add node. Return true. Put node in graph. Range length graph. Visited is equal to set. DFS node visited res. And we return sorted res. Oops, we forgot to pass in our adjacency list. Missing 3 required positional. Node adjacency list. Oh, node adjacency. Okay. We were so close, man. Oh my gosh, dude. We had the right base cases for neighbor and adjacency list. If not DFS. Would it be the same if DFS is equal to false? Just make it easy to read. Okay. So if DFS neighbor JC has visited res is equal to false, we return false. Otherwise, if it's not visited over remove, we notice process, we add, and we return true. Then down here, if DFS we were close. We had the right thinking. Holy shit, man. Our thing is so bad. Like, there's so much faster solutions, dude. Like, let's submit this, bro. I'm kind of proud of this solution. Let's get like the rocket emoji again, bro. We gotta make the clickbait title, dude. I think it's O of V plus E. O of V plus E. Ooh. O of V plus E. V plus E. All right, we're gonna end it there. Appreciate you guys watching. I will see you tomorrow.